Hi, this is Nasnianowski, and we're going through monoidal category theory. We're up to section 4.6, and chapter 4 is about connections between two categories. We dealt with we dealt with equivalences, we dealt with adjunctions. Last class, section 4.5, we dealt with exponentiation, functor categories, and common categories. We'll use them here in this section. So what are we doing here? We're talking about limits and colimits revisited. Okay, so in chapter 3, we spent a lot of time talking about different ways of talking about limits and we talked about limits and colimits. Basically, remember, we had covers, and we're basically talking about the best fitting covers, or colimits are the best fitting co-covers in some sense. Okay. Then, in chapter 4, when we talked about adjoint, we saw that some limits, like initial objects, terminal objects, products, and coproducts, could be done, limits and colimits. Some limits and colimits, initial objects, colimits, terminal objects, limits and products and coproducts, can be done very nicely with adjoint functors. And now what we're going to do is we're going to look at all types of limits, any type of limits whatsoever, and we're going to show that they're also done with adjoint functors. Okay, so that's the purpose of today. We're going to generalize and talk about any type of limit whatsoever, and we're going to get that. Okay, great. So again, what we're just to reiterate, what we're going to do is we're going to show that any type of limits can be done with adjoint functors. Okay, so we start off with a diagram category. Let's remember what a limit is. A limit is some type of shape of things in a category, of elements and morphisms in a category, okay? And then we pick one particular element, and that is somehow covers all those things, okay? So it's the cover of the pot, okay? And it's the best fitting cover. Okay, so let's just get something straight. Okay, D is going to be a diagram category, okay? And just for the hell of it, the book has an example of a diagram category. I have a shorter example. It's going to be something like this. Okay, the category, something like this. Okay. Now, just to remind you, there's a unique functor from here, from any category, into there. But what we're interested in is the contravariant version of that. Okay, and that goes from B to D. And B to 1, and this goes the other way. Okay, we call that delta. Okay, and that is the diagonal map, basically. Okay, so we're going to have to use that. Okay, great. Now, let's look at this category. We're going to spend the entire section in this category. So a typical element in here is a functor from D to B. Okay, and basically what it does is for every object here, it picks out an element here, and for every morphism here, it picks out a morphism here. So a typical element will look something like this. B1, B2, I'm going to give these things names. B3, okay. Okay, like that, and we'll call this B4, because we're not too creative with our names, okay? And also, not only does it pick out objects, but it also picks out morphisms. So we might call this F, G, H, K, I don't know. Okay, these are morphisms in K. Okay, so that's a typical element here. Now, question, what's a typical element here that's from this functor? Okay, and typical element here from this functor is as follows, and I'm going to draw it over here. Didn't do my spacing very well. It's going to be something like this. Here's a typical element there, B, okay, and we're going to have B, and then 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 here we're going to have identity on B. This is not intelligent. Identity on B, identity on B. Okay, so again, within this category, this functor category from D to B, here's a typical element there, and here's another element there. Okay? I'm sorry. And here is a typical element in here from this functor. It's in the image of this functor. Great. Okay? Now, this is a very cute diagram, but in essence, really what it is just B. Okay? The identity morphisms are just identity morphisms. They don't change anything. Okay? Okay, great. Okay, question. What are the morphisms in this category? So let's go through this. The objects of this category are functors from D to B. The morphisms are natural transformations between those functors. Okay? Well, basically you have one object here, okay? You have many objects. You can think of it as a diagram that I just erased, but basically a natural transformation is morphisms from here to there. So basically, you're going to have a morphism like this. This is all in B. You're going to have a morphism like this. You're going to have a morphism like this. And you're going to have a morphism like that. Okay? So that is a natural transformation from this to this. Okay? So let's write that out. It's a natural transformation from the delta of B to F. Okay? And we write that like that. Okay. First, these things are called a cone of F. I'm sorry, they're called a cone. It's called a cone. Okay, very nice. That's a cone. Okay, second of all, we've seen such a picture before in chapter 3. This is what we called a cone on a cover on top. So that's a typical thing that's in this category of B to D. Okay, now you might have another cone. Okay, so here's another cone. It's going to be another object, delta of B prime. Okay, so we're going to have a B prime there. And again, you can make this B prime, B prime, B prime, B prime, identity of B prime, identity of B prime, etc., but you can draw it also as one object category. Okay, and a morphism from there till F is like this. It's going to pick out every single object. It's going to be another cover, just like before. And again, all the things have to commute. Very nice. Okay, and now we could talk about, not only can we talk about, very good, so here's a cone over F, here's a cone over F, and now we can talk about a morphism of cones. So there's a new concept. So the morphism of cones is a morphism in B such that all these triangles commute. Not only, so again, all the cones make sure that everything commutes with the F, G's, and K's. But here's a morphism between cones, so it's a function from B to B prime, such that this triangle commutes, this triangle commutes, this triangle commutes, lots of triangles commutes. Okay, great. Guess what we do? Now that we have this notion of a cone, and now guess what we're going to do? We have the notion of a morphism of a cone. So over F, by the way, all that we didn't change. So now we can talk about the category of cones over F. Okay. Okay, great. Okay, good. Okay, so we have the category of cones. Guess what? We can, and we always do this in category theory, what we can do is we can turn the whole thing upside down. Okay, and instead of talking about morphisms to F, we could talk about something else. Here's a typical element in B to D. And now I want to talk about functions from this typical element to this typical element. Okay, and guess what it'll look like? Well, you don't have to guess because it's, well, let's redraw it, okay? You know what? Let's redraw it. So we're going to have B1, B2, B3, B4, boom, 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 boom. Okay, and we call this f and g and h and k. And now function from there to b, well, again, delta of b, you can draw it with 4 different objects, so you can draw it like that. And a natural transformation just brings this to this. Okay, and of course you could have 2 cones. I'm sorry, so this, we need a name for this. Such a thing, a natural transformation from a functor to the diagonal of a functor is called a cocone. Okay, and of course you could have 2 cocones. Ba-dum, ba-boom, 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 ba-boom. 2 cocones. And you can have a morphism between 2 cocones. And guess what you have? You have a category called cocones. I wouldn't say over F, cocones of F. In fact, the way to think of it is F is over them. So I guess it would be cocones below F. And here we'd say cones above F. Okay, this is a search for an adjective. Very nice. Okay. Okay, so we've turned the whole thing upside down. Great. Now let me tell you what a limit is, and let me tell you what a colimit is. I'm going to show it here, and then we'll see this again. Ready? A limit is a terminal object in this category. In other words, if there's any other cone that fits very nicely, then there's a unique morphism like that from that other cone to this. So we're going to say B is a limit of F of the diagram. If there's any other cone, then there's a map like that. Okay, but I used this expression before. Okay, I used this expression before in chapter 3 when we talked about covers of a pot, and then we talked about the best fitting covers of a pot. Okay, so that's exactly what we have. We have the best fitting covers of a pot. Okay, great. So I'm going to do this. I'll write it down more formally in a second. Great. What's a colimit? Very simple. Okay, a colimit is an initial object in the category of cocones. So we're going to write that as that. Take this B out. I'm going to write a colim of F, that's your diagram, okay, is a map from the diagram to the colimit. Furthermore, it has to be the best fitting colimit. I'm sorry, it's the best fitting cover from below, okay? In other words, if there's any other good fitting thing, there's a unique map from there to there. Okay. Okay, so I'm basically restating what I said in chapter 3 about good fitting covers and best fitting covers, but I'm doing it now in the language of functor categories and talking like that. Okay. By the way, we did this once before. Once you have something, an initial object, a terminal object, they're unique up to a unique isomorphism. Hence, all limits, all colimits are unique up to a unique isomorphism. I'm just bringing it out. We did this. That was the first thing we did about in chapter 3. Limits and colimit. I'm sorry. Initial objects and terminal objects are unique up to unique isomorphism. Okay, great. Now, I explained what this category of cones are. I explained what the category of cocones are, but what I want to do now is I want to show you how to build them formally, okay? And that's not hard at all. It goes as follows. Again, our entire discussion happens in this category, okay? And fundamental to this category is this delta, okay? Namely, what we're interested in is things that are of this image where basically the single object points to everything else. So we're interested in this, but we're also interested in some constant function, which we might call, I don't know, it's the thing that picks out f. It's the thing that picks out F. So let's call it constant on F. What do I call it in the book? Yeah, I call it constant on F. Const on F. Okay? And so basically what you're doing here is you're looking at the comma category. Okay? Look at all the elements here that come from diagrams of this form, and look at all the single element here that looks like that, and you take the cocone, you take the comma category, delta comma constant at F, okay, and this is the cones of F. Very nice. Okay, if you swap these around, let's do it. 1 constant on F, B to D, okay, boom, delta B, okay, and you look at the comma category here. Let's just see what this is. This is functions from F to any diagram here. What you get is the cocone category. The cocone built on F. Okay, great. Okay, so now I showed you how to build this category of cones over F, and category of cocones below F. Right. Gotta be careful with your adjectives. Okay, great. Now let's make a formal definition. The limit of F from D, that's a shape category or a diagram category, to B is a terminal object in cone of F. Of course, it's not unique. It's unique up to a unique isomorphism. Okay, let's just do this again. The colimit of F is a initial object in cone of F. Okay, and that's it. So we revisited, we have a few more things to do here, but we just redid all of limits and colimits in 15 minutes. Okay, but it's a very beautiful construction. I mean, this functor categories are a very beautiful construction. Okay, now if you look at it carefully what it's about, and the book goes through all the details, we have a diagram that we're used to already. Okay, namely, this goes here. Okay, and if you take a functor here from B to D, okay, and you look at the limit of that functor, that's an object in here, okay, then colimit. Okay, then we have these two adjunctions. Okay, and again, whenever you see, you have to go through what the Ham sets look like. You also have to go through what the units and co-units look like. But this is very much similar to what we saw before with limits and initial objects and terminal objects, and products and coproducts. So it's the same diagram all over again. And this statement that we said that the limit is unique up to unique isomorphism, that corresponds to the fact that this adjoint is unique up to a unique isomorphism. Okay? The fact that colimits are unique up to a unique isomorphism corresponds to the fact that left adjoints are unique up to a unique isomorphism. So all these different concepts all over, they're really the same thing. They're stating the same thing. Okay, great. Let's say you have a functor from B to C. Okay, and we'll call it G for a second. And what you can do is, not only can you have a diagram from D to B, okay, but you can also talk about diagrams from from C to D. Okay, I don't want to mess up this diagram. I don't want to mess this up. What we can ask is whether or not limits are preserved by G. Okay, so what does it mean? That means if you follow this, you take the limit, then you do that, G, well, you can not only have limits here, but you can have limits further on. And a limit is preserved if the following is true. G of limit of f is equal to the limit of G composed f. Again, we have to talk about D to the C and talk about how limits are related to that. Okay, but I don't want to get into that. What I just want to say is this is what it means for a functor to preserve a limit. And of course, we could also talk about a functor preserving a colimit. So one thing is preserving. Okay, great. Okay, but you can go on. Okay, and not only talk about preserving, there's also a concept of reflecting. Okay, let me tell you what that's about. Let's say I take a diagram in B and I take G of that diagram. So then I get a diagram in C. Okay, and now one object is the limit of that diagram. G reflect, not a question, definition. G reflects limits. If G of the limit is here, then it's here also. In other words, what goes to a limit must come from a limit. So it's not only it reflects, in other words, if it went to a limit, then what it went to that limit is also a limit here. So these are requirements. Sometimes G has these things, sometimes G does not have these things, but we can always ask whether it's true or not. Okay, but again, what you should really do is you sit down and work this out in terms of another diagram like this. So you're going to have C to the D, and you're going to have C, and you're going to have delta of this, and you're going to have G over here, and here you're going to have what? Okay, and you have to work it out in terms of that. It's a nice diagram. I'm sorry, this is not in the book, but it can be easily worked out. This is G lower star, right? This is G lower star. So if I have a functor from D to B, and I follow that from B to C, I get a functor from D to C. Okay, let's just write this out. If I start here, take the limit, do G of it, that's the same thing as pre-composed with G or post-composed with G. So take the functor here, post-compose with G, that gives you this. Take the limit here, this commutes. Okay, so that's what preserving means. Sorry, I should have done that in the book. That's a really nice thing. Okay, what does reflecting mean? Okay, reflecting means as follows. Start with the diagram here, do G of it, take the limit of that, okay? If G takes you to the limit here, it must have been that this came from a limit. So that's very nice. Anyways, that's a very pretty diagram. Okay. Okay, let's erase it. Okay, two theorems. Write adjoints preserve limits. Left adjoints preserve colimits. Okay. Right adjoints preserve limits. The book goes through a technical definition, but I think just by doing this, you can do it the same way. So I didn't check this, but I just tried it. Basically, it goes as follows. Here's limits. Okay, if you have G, if G is a right adjoint, so then this is a right adjoint composed with a right adjoint. The composition of two right adjoints is a right adjoint. Okay, and here you have G lower star. This should probably be H lower star. Okay, looks like these two should be adjoints also, and so composition should be also right adjoint. But what you have to do is you have to show that how does it go? That they're right adjoints, so they're both right adjoints. So here we have two ways of writing right adjoints from here to here. The limit, and then this right adjoint, okay? And then G lower star, and then the limit. Okay, what we have to show is, so those are two right adjoints from B to from DB to C. Very nice. Okay, but what we have to show is that these ways of going back are really the same. So let's just see what it means going back. It means delta, and then H is the same. So delta means basically make this diagram one thing, and then do H of that single diagram. Okay, that's going to get you there. Okay, and then H basically is that, and then do the whole thing. So I think that's the way this is the right way of proving that right adjoints preserve limits, left adjoints preserve colimits. You have it right there. Okay, I'm sorry, I didn't write it in the book. I should have written it in the book. That's really the right thing. We're going to see lots of diagrams like this in section 4.8 when we talk about logic. Okay, let's talk about completeness. Good, so now that we have a nice clear description of what we mean by a limit and colimit, let's just say the following thing. A category, again, we're making definitions, is finitely complete if all finite D in other words, the shape categories have limits. Okay. Another name for finite complete is has finite limits. Okay. So we can talk about having finite limits. So we say it's finitely complete. Okay. Now we can generalize that, and before we do that, a category is finitely co-complete if all finite D have all colimits. Very nice. Okay. So that's one thing. So finite limits, finite colimits, but we can also talk about a category is complete, okay, if it has if for all D, no matter what size D is, maybe it has to be locally small or something like that, has limits. Has limits. Okay, so we could talk about complete, and then of course we could talk about co-complete with colimits. A category is co-complete if all D has colimits. Okay, for any shape diagram whatsoever. So we have finite limit, finite complete, finite co-complete, complete, and co-complete. Okay, let's just talk about a category is complete. There's a generalization of a theorem that we did. A category is complete. Okay, if it has all products and equalizes. Okay, a category is co-complete. This is a theorem. Co-complete if it has all co-products and co-equalizes. Okay, and again, you can make changes in terms of, instead of co-equalizes, you could talk about push-outs and pullbacks, et cetera, et cetera. There's a whole, lots of different definitions, lots of different theorems showing these different things. Okay, great. Okay, I just want to talk about the last important categorical ideas, and it's called the many ways of describing the structures, okay? And it's kind of a summary of what we saw so far, okay? And so it talks about three different ways we saw of describing structures, okay? This is our 17th video together. So we had three different ways. One is universal properties. Okay. Namely, tell me, what does this structure satisfy in terms of all the other objects in the category? What is it about it that it has? Okay. Two, okay, we talked about limits and colimits. Okay, namely this covering of the pot, or co-covering of the pot, or what's the best fitting cover of the pot, okay? So that's another way we talked about, and we showed that a lot of different things are limits and colimits, okay? Including products, co-products, equalizers, co-equalizers, pullbacks, push-outs, et cetera, okay? The third thing we saw, chapter 4, section 4.4, is adjoint functors. Okay. In this thing, I show, basically what we did today was show that limits and colimits can be written in terms of adjoint functors. Universal properties is just another way of writing limits and colimits. Okay, so all these three things are saying the same thing. So if you have some structure and you could describe it with universal properties, then you could describe it as a limit or colimit, and you could describe it with adjoint functors. Similarly, if you have some structure that you can describe with adjoint functors, you can describe it by the other two. Similarly, if you have some limits and colimits, you can describe it by the other two. So all these three things are just three different ways of saying the same thing. Very good. We're going to see in section 9.2, there's going to be a fourth way of doing this, and that's something called con extensions. Okay, and all these things can be done with con extensions, although con extensions are much prettier. Okay, takes time to get used to them, but they're much prettier. Just like this adjoint functor way of looking at limits and colimits is much prettier than just looking at colimits. Okay, con extensions is a prettier way of looking at everything, but it takes time to get used to it. But once you get used to it, boom, it goes. Okay, and also, con extensions, not only can con extensions talk about these, this, and this, but all these things can be written, can describe con extensions. Con extensions are certain types of functors that have universal properties. They are certain types of functors that you can look at as limits and colimits, a little bit more complicated. The con extensions are in particular a type of adjoint functors. So we'll have that. Anyways, so lots of stuff coming up. But it's just, again, the power of category theory. You have three different ways of describing things, and they're all describing the same thing. So whichever works, you're going to need to use whichever works. So that's section 4.6. 4.7 is about the Monoidal lemma, which is one of the most fundamental theorems in category theory, and we'll talk about that next. And then 4.8 is about logic, doing logic with adjoint functors. Basically, categorical logic, which is logic with adjoint functors, which is all about that. Okay? Okie doke. Have a wonderful day.